Hello, my name is Gregory Foster. My project is network telemetry anomaly detection with stream learning. In plain terms, this project uses machine learning to detect abnormal network behavior from router and switch data as the data arrives over time. I'll cover the problem, motivation, through the conclusion, the future works, and my contributions. I'll also define networking terms as I use them. Modern networks produce telemetry, which means measurements exported by routers and switches, such as routing state, interface counters, timestamps, and protocol behavior. The main target is BGP clear. BGP means Border Gateway Protocol, the routing protocol networks use to decide how to reach other networks. A BGP clear resets a BGP routing session, so routes may need to be withdrawn and relearned. I also evaluate port flap, which means a network's interface repeatedly going up and down. Um, so this is difficult for five practical reasons. First, labeled anomaly data is limited. Secondly, the detector must work in a stream. It has to work in one pass over the incoming data. Third, false alarms matter because operators will stop trusting a noisy system. Fourth, smoothing alarms can reduce noise, but they can delay detection. Fifth, feature choice matters because routing events should appear most clearly in routing related telemetry. The primary paper I reproduced is telemetry-based stream learning of BGP anomalies by Putina and co-authors. Their idea is to model normal telemetry behavior with streaming clusters and treat points outside those clusters as possible anomalies. The algorithm foundation is Denstream. It is unsupervised, so it does not need labeled training examples, and it is online, so it updates as new samples arrive. I also reviewed supervised BGP anomaly detection and normal behavior deviation frameworks. But Denstream fits this project best because the labels are limited and the data arrives over time. So the full run uses five node level Cisco and big DAMA telemetry data sets and ground truth event windows. Four data sets are BGP clear scenarios, and one is port flap. A node means one network device, such as a leaf or spine router in the testbed. Ground truth is used only after detection to score alarms, not during inference. The pipeline starts by loading telemetry CSV files and matching ground truth files. Pre-processing converts usable columns to numeric features. It fills missing values, removes constant columns, and we also create three feature groups in the pre-processing steps. So the three feature groups: control plane, data plane, complete features. Control plane features describe routing and protocol behavior. Data plane features describe forwarding or traffic behavior. And the complete features uses all usable numeric features. Normalization. Normalization is fit only on the initial baseline period, which reduced leakage from future anomaly samples. Then Denstream processes each sample online after that. If a sample does not fit a normal microcluster, it becomes outlier evidence in the Denstream algorithm, and the alarm logic turns that evidence into time-stamped alarms if it aggregates over time. So the existing work supplied by the paper, uh, data sets, feature mode idea, and Denstream foundation. Uh, my work was building a modern Python 3 reproduction around that idea. I implemented dataset loading, ground truth alignment, pre-processing, baseline only normalization, Denstream style online detection, temporal and spatial alarm rules, DB scan, and mini batch k-means baselines. Um, Validation logs figures in the final analysis as well. The evaluation is based on alarms and events, not regular sample accuracy. Alarm precision means the fraction of generated alarms that overlap a real event. Event recall means the fraction of real events detected by at least one alarm. Alarm event F1 balances those two. I also report false alarms per hour, detection delay, alarm count, detected event count, and runtime. The strongest result was Denstream on BGP Clear second, using control plane features and temporal alarm aggregation with K equals 4. Here, K is the threshold for how much outlier evidence is required before raising an alarm. If you're familiar with K nearest neighbors. This reached alarm precision of 1. The event recall was 0.875, an alarm event F1 of 0.933, and it produced 0 false alarms per hour with a mean detection delay of 29.57 seconds. Practically, it detected 7 or 8 events with only 8 total alarms. Denstream was the best streaming detector. dbScan is another density-based method that can label low density points as noise, but here it sees the full node matrix, so it is not an equal streaming competitor. Mini batch k-means is a faster clustering baseline, but it assumes data fits around cluster centroids. And Denstream had the best balance of precision, recall, and streaming realism as the cluster centroids with Denstream adapt over time dynamically uh, online. So the results match the network domain. BGP clear is a routing control event, so control plane features were the most useful. The BGP clear datasets reached much stronger F1 scores than port flap. Port flap was harder because it is an interface event rather than a routing session reset. That suggests interface anomalies may need interface specific features, in interface specific preprocessing or a separate detector tuning. The main operational trade-off is temporal versus spatial alarms. Temporal means the same node must show repeated outlier behavior over time. Spatial means multiple nodes are outliers at the same timestamp. Spatial k equals 1 was very fast. It detected every event on the best data set with a mean delay of 2.63 seconds, but it produced 110 alarms and many false alarms. Temporal k equals 4 was cleaner. It reduced alarms to 8, removed false alarms, and still detected 7 out of 8 of those events. So this project reproduced the central idea of the primary paper, which is that unsupervised stream clustering can detect BGP anomalies from high rate telemetry and turn outliers into useful alarms. The strongest setting was Denstream with control plane features and temporal smoothing. Future work could be done on the remaining Cisco scenarios, tuning Denstream parameters more deeply, compute confidence intervals, improve port flap detection for sure, and add alert prioritization so operators can choose between fast spatial alarms and cleaner temporal alarms. To close, the existing work includes the Putina paper, Cisco telemetry datasets, the Big Gamma reproduction code, and the Denstream reference implementation. My work was the modern implementation, pre-processing, alarm logic, baselines, metrics, experiments, figures, validation artifacts, and final analysis. Thank you.